It's a pleasure to introduce. Many of you know him, but maybe some of you not so much. Nicolas Laporte is a French postdoc who has been working in my group for the last year, a little bit of a year, I think. He's moving soon to the south, to Chile, to the Católica, where he has got his second postdoc position. Nicolas studied physics in Clermont-Ferrand in France, where he's from. Then moved to Bordeaux, isn't it? Bordeaux to do the master in astrophysics. And then from Bordeaux to Toulouse to work with José Pujol, that many of you know, to work on his thesis on studies of the highest redshift objects in the universe, highest redshift galaxies, studying the so-called Woods field that is based on WIRCAM data, near-infrared data from CFHT, and also clusters of galaxies. So here he has been involved in Herschel Spire, the group I'm leading, particularly in the Hermes project. In the last months, his main project has been this, and the results he's going to show you here is based on the first frontier, the first observations of the first cluster observed as part of the frontier fields. The frontier fields is something new. It's probably the first time you hear talk about this. But this is the flagship program of Hubble, Spitzer, and Chandra for the coming 3 years. So, as we have heard in the previous talk this morning by Barry Mador, Spitzer, for instance, has been, of course, Hubble as well, have revolutionized astronomy in the last decades. This is a new project that is starting to revolutionize astronomy also at the highest redshifts, because it's going to be the deepest observations with Hubble and Spitzer of clusters of galaxies, and massive clusters of galaxies, and the best ones for using gravitational lensing with magnification factors up to 100 or more. So basically, we are using data that the equivalent is something like a Hubble telescope in space of 100-meter diameters, or a Spitzer telescope of 80 meters in diameter. Okay, I don't going to tell much more. I like to give the talk, but it's his talk today.
No, I have one. Thank
Sorry.
you. Okay. Yeah, now, is it better? Okay, sorry. And I will describe in detail the results that we published last week on a redshift 8 galaxy candidate. But before that, let me present you the team who analyze the data and contribute to the results we publish. So here at the IC, you have Ismael, of course, Alina, Paloma, and Rui, and myself, of course. And we worked with people from Switzerland at the observatory, at the Geneva Observatory, and at École Polytechnique de Lausanne, also from France at Toulouse and Lyon, and from the US at the University of Arizona. So let's start now with the frontier fields. So the main goal of this program, of this new project, is to explore the early universe. And when I say early universe, I mean to study the first billion years of our universe. And in terms of redshift, it means redshift beyond 6 and up to 10, 11. Let's see what the result will be in the coming months. But and they plan, the frontier fields team plan to observe 6 clusters of galaxy and 6 amplify, to combine these two fields of view. And why we need to observe a cluster of galaxy? As Ismail mentioned at the beginning, if you put a strong mass, a strong lensing cluster between your telescope and the first galaxy, let's say, the object at very high redshift, you will amplify the light. Due to the strong mass of the cluster, you will amplify the light coming from this background source. This is what you have here on the animation. And one of also of the goal of the frontier field is to provide the deepest image for the cluster. So we will reach a depth comparable to the Hubble Ultra Deep Field. I will give you the detail of this depth just after. But it will be the deepest image. So, and also the good point is that all the data are public. So if you have observation during the week, you will have the release, the final, the high-quality data at the end of the week, released by the Space Telescope Science Institute. So, more detail again. These frontier fields involve 3 telescopes. The Hubble Space Telescope and its 2 cameras, ACS working in optical, and the Wide Field Camera 3 working in near-infrared. Also the Spitzer Space Telescope with IRAC and the Chandra X-ray Observatory. On the picture you have just here, you can see the field of view. So the blue square show you the field of view of the ACS camera. You see the Abell camera working in optical. The red square is the field of view of the Wide Field Camera 3. This is the near-infrared data. And more or less the size of the pictures is the field of view of the Spitzer data. So the first observation have been made in September for the Spitzer data and in October for the Hubble Space Telescope observations. The first release, you have to know that there is no release for the Spitzer data. You have access to the raw data, but up to now there is no release. You have to download the data and reduce by yourself. But for the HST, for the Hubble data, as I mentioned, the Space Telescope Science Institute produce new data every week. So every Friday you have new data, new set of data, if observation have been made during the previous week. So that's really interesting. And here you have, okay, the wavelength coverage of the HST data, so from 400 angstrom to 1.7 micrometers. And you can add to that the Spitzer data. Yeah. Absolutely, yeah. Yeah. You have the cluster map, you have the lensing map, you have all. Already, yeah, you can access to, and I think you have already the amplification map for all the clusters already. So I will give you the link at the end where you can download all the data, etc. So you have the wavelength coverage. You have here the 6 clusters planned to be observed. 3 clusters are in the northern hemisphere and 3 in the south. And you have on the table just here, you have the expected depth. So you see that it's, we plan to reach a depth of 29 AB magnitude at 5 sigma, the deepest image around the cluster of galaxies. But you can see that the full release, the first full release, will appear on the website, on the internet, in July 2040. But we can already use this data because the release in December, the Hubble Space Telescope released the first Wide Field Camera 3 data and the full data. So we have 100% of the Wide Field Camera 3 data planned for the Abell 2744. So we use this data and we combine this data with previous optical data, so you can find the data in the archive. And if you combine this previous data with the frontier fields data, you can increase your wavelength coverage and you can start the search for the first galaxy. This is what we did here. So our main objective was to search for this very first galaxy. We apply the Lyman Break technique, which is one of the most popular methods to select very high redshift candidates. It's based on, you see on the animation here, the shape, the evolution of the spectra shape here, from redshift 3 to redshift 12. And if you remember, my goal is to study the early universe, so beyond redshift 6. And if you just have a look at the shape of this starburst spectra from redshift 6 to redshift 12, you see that we should have a non-detection at short wavelength, a strong break, then a detection, and specific color after the break. So this is the criteria we impose. This is the Lyman Break technique. And the kind of color we can use are shown here on that plot, coming from the Richard Bowen's paper in 2012, and looking for redshift 8 objects. So the gray region here show you the expected color for this kind of galaxy. The blue line are the expected color for a starburst from redshift, so at very high redshift, and as a function of the UV slope, so -3 or -2. And, okay, just have a look at the green region here. where the dwarf, the MLT dwarf, are expected. So our sample can be contaminated by dwarfs, but I will discuss that at the end. So now let me show you the data we use. So I remind you that we use all the wide field camera 3 data from the Frontier Fields program, so from 1 micrometers to 1.7 micrometers to a depth of more or less 29 at 5 sigma. And you have also the ACS data we use. This is previous observation in the archive here from 400 angstrom to 900 angstrom with a relatively, of course, relatively a small depth. It is smaller than the wide field camera 3. We know that if we impose a strong break, because you remember the shape of the starburst spectra, if we impose a strong break, we will remove most of the contaminants, which are the low redshift interlopers. So we impose a strong break. And regarding the property of our data, this strong break, so we impose 2.5 magnitudes, non-detection in optical, strong detection in near infrared. The detection criteria we use are non-detection at least 2 sigma in optical and a strong detection in the near infrared, so more than a 10 sigma detection. Of course, we start the search for the redshift 10 object, no bright 10 object in that field, non-redshift 9 object also, one bright redshift 8 candidates, several redshift 7 and several also redshift 6 objects. So let me show you the distribution of that object over the field. Here you have the cluster fields. It is the wide field camera 3 field of view. The red line shows you the critical line for the redshift 7 object. The yellow line shows you the position of the multiple images are expected for a redshift 7 candidate. So all these objects, redshift 7 and redshift 6, will be presented in a forthcoming paper led by Akimatek from the Lausanne University. And for the rest of my talk, I will focus on the redshift 8 object, which is here on the 8 of the image. You can see, yes, on the animation. So this is a redshift 8 candidate. If you remember the criteria I imply, yeah, we have a strong break. Here you have the shape of these candidates in the ACS data. Here in the wide field camera 3. So strong break. You have the photometry here. It's a very bright object, 26.2 magnitudes. For a redshift 8 object, it's relatively bright. And one interesting thing that we can show using the Abell data is the morphology. The morphology of that object. Here you have a zoom, and you see that we have a clumpy morphology. And this is exactly what is expected for a redshift, for a very high redshift object. So that's another argument to say that we have a good candidate here. So remember that I say that the Frontier Fields program combines Hubble observation and Spitzer observation. So we reduce Spitzer data. Alina did reduce the Spitzer data. And this is the shape of our object in the Spitzer data. So once we reduce the data, we get 2 images, one at 3.6 micrometers, another one at 4.5 micrometers, with relatively similar depth. This object is non-detected at 3.5 and strongly detected at 4.5 micrometers. How can we explain that? In fact, if we go to that paper, the Smith et al. Paper, where you have an explanation, a kind of explanation of what's happened in the Spitzer photometry for the very high redshift object, you can see here at redshift 8 that the photometry at 4.5 could be contaminated by strong H beta and O3 line at very high redshift, at redshift 8. Okay, so this is another good point to say that this candidate, if we combine the large break, the flat photometry after the break, and this non-detection at 3.6 and strong detection at 4.5, is another argument to say that we have an excellent candidate at high redshift, at redshift 8. So using all the photometry from the ACS, wide field camera 3, and Spitzer, we perform a SED-fitting work, spectral energy distribution, fitting, using the new version of Hyper-Z. This is version 12. Now the version is public. You can download it if you want. Using, of course, template, including nebular emission, because we suspect that the photometry at 4.5 is contaminated by O3 and H beta lines. So we perform the SED. 2 cases, one allowing a large range of redshift from 0 to 12, and another one assuming, let's say, a low redshift solution. In black, here you have the results. In black, the black line here show the high redshift solution, redshift 8, plus minus 0.3. And in the magenta line here show you the low redshift solution, 1.9. And as you can see, it's difficult to explain the non-detection in Spitzer. Here we put a 3 sigma limits to be more conservative. So it's difficult to explain the non-detection here with the low redshift solution. So it's another argument to say that the photometry of our object seems consistent with high redshift solution. Here you have the redshift probability distribution, the black line here. We have one strong peak. We say without secondary solution. In fact, we have a secondary solution, but the integrated probability is less than 1%. So again, this is completely consistent with high redshift. And now the property. Once we have the redshift, we can play a bit with the metallicity of the template and deduce several properties, such as the star formation rates. So we give you range of star formation rate from 8 to 60 solar mass a year. The same for the rending, the stellar mass. Of course, we can estimate the equivalent width of the O3 and H beta line, okay, which seems that seems contaminate the 4.5 photometry. And the good point is that all these values are consistent with expectations for redshift 8 object and previous results. Remember that I mentioned that our sample can be contaminated by dwarfs, but our object is clearly resolved on the HST data. So the star hypothesis is clearly unlikely. So we try to measure the size of this object using Galfit and Sextractor, and the results are relatively similar, 0.3 kiloparsec. And the last step that we can do using photometric information is to compare the density of object we found in that field, one object, one bright object at redshift 8, with previous density observed, for example, in the Hubble Ultra Deep Field, etc., but with very faint object. And here you have the luminosity function at redshift 8. The luminosity function show you the distribution of the galaxy as a function of luminosity for a given range of redshift. So here you have the very bright object, and here you have the very faint object. And our object is here. We have one object in a very small field of view. This is why you have a very large error bar, because of the cosmic variance. And it seems that we are consistent with also with the trend observed since 2012 by the etude of Pascal Hoche using the Hubble Ultra Deep Field. So, just a brief conclusion. So we find one bright redshift 8 candidate, and that's really important to mention that this is a bright redshift 8 candidate. Because, okay, so the property of the galaxy, so large break, non-detection in optical, strong detection in infrared, plus the non-detection at 3.6 and the strong detection at 4.5 seems consistent with the redshift 8 object. And why is it important to say that our object is bright? Because the next step is to confirm this object by spectroscopy in a reasonable amount of time. I mean, within 15 hours, you can, or we hope to be able to confirm this object using, for example, X-shooter and CMOS. This is spectrograph in the south. And I think that I mentioned him here, not for that object, because that object is in the south, but I'm sure that EMIR, if you remember the scheduled program for the frontier fields, you have two clusters in the north observed in 2016. So if EMIR is available in 2016 or even after, I'm sure that EMIR could play a strong role in the study of the frontier fields. I mean, in the confirmation of the very high redshift object found in the frontier field. Of course, this is exactly the science case of the James Webb Space Telescope 4 years from now, and maybe also from the ELT for the very faint object. But the James Webb, I suppose, will do a lot of job before. So the link, if you want to download the data, you have the data, the lensing map. You have also the astronomer's blog if you want to follow, let's say, the results from the frontier fields data. And because it's funny, I want to show you these two websites because we have been the first to publish high redshift results using the frontier fields data. And NASA made a lot of publicity of our work, so we have been published on the first page of the NASA website, the first page of the Abell website, the GPL, so, okay. That's a redshift 8 object. It's not the most distant object. It's one of the most, one of the brightest, but, okay. And I think I can stop here. Thank you.
Thank you very much, Nicolas, for this nice talk. Time for questions.
Concerning the morphological aspect of the object, you said it is sort of clumpy.
Yeah.
But there are two questions. One is, have you taken into account that you are looking at it in the ultraviolet? Because I mean, yeah. And also, well, the objects used to be clumpy as well. And also, it's not a distortion due to lensing. Also
no, because we are very far from the cluster core. So the amplification factor is very small, so it's something like 1.5. The amplification is very modest, so the distortion is not expected to be very, very huge. So no, I don't expect that this is due to the distortion. And about the morphology, we try to just measure the photometry from the main object. Let's say that one. You have these two objects has the very similar colors, so it's difficult to, we are observing in the UV, so we can have different emission part of the galaxy, but no, we don't make a lot of study on that.
A small question about the general program. Why do they repeat a couple of clusters that were also included in the clash observation? They were very deep already, so they are repeating them again?
Yeah, they will go 1 magnitude deeper. 1 magnitude deeper. In clash it's 28, and here we plan to go to 29. So 1 magnitude deeper could increase strongly the number of very high redshift objects. I mean redshift 9, 10, I think. Yeah.
Because of those previous observations, the mass models are the best ones. It's been about 1 year to define this program. There are a lot of
Yeah, I have a question connected to the estimation of the mass and the sizes here, because it's not only that you are observing in the ultraviolet, but also if you trust that the object is a redshift 8, that implies that you have a cosmological dimming of almost 10 magnitudes. So that implies that as most, you are observing the peak of the of the emission of the galaxy, so the bulge or whatever is there. No? You always have to make the assumption that you are observing everything. Otherwise, otherwise your mass could be wrong by a factor of 10. Your size is also. So if you take a normal galaxy, for example.
Yeah, I see what you mean. We just play with the metallicity to give the large, to give the interval on the mass and on the size. Yeah, this is the UV size. We cannot,
No, but it's not only that. I mean, it's that you are missing all the low super brightness features. Not so low. I mean, you have 10 magnitudes of cosmological dimming. So how many magnitudes are you able to observe of this object in terms of super brightness? A couple of magnitudes. So you see my point. So maybe when you say the effective radio is 0.3, maybe you are not even reaching the real effective radio of the object at all. So
No.
Unless you assume that the object is extremely compact. But if the object is not compact, you are basically missing 90% of the light or so. So this is something that it should be always in mind when you provide numbers like this. I mean.
Yeah. This is a reducing UV.
And I have a question concerning the star formation rate and the lifetime of this galaxy. Because, I mean, these numbers are quite similar to those published by also, I mean, recently there is a paper, I don't know if it is Nature or I don't know where.
Yeah, at 9.6.
Yes, so it was, I think that the star formation rate was a bit higher. The mass was about that. The redshift was about this.
Yeah.
And these people found that the time to build a galaxy like that was about a million years, several million years.
Yeah,
or so. So what is the number you get? I mean, how long does it take to form a galaxy like this?
For the age?
Yes.
That's a good question. I don't remember. It's in the paper. I don't have the number here.
But the number is like 100 megayears. So
Yeah, maybe.
time scale, I mean, if you divide the mass, but star formation rate,
Right.
10,
In an instantaneous star formation?
Yeah.
Right?
you need like 100 megayears to produce that mass.
Which is very short.
Yeah. And maybe also the object is starting to produce a star.
That's right.
So and then it peaks at 34 stars.
Okay, I just wanted to see if you had made a comparison with similar objects.
Yeah.
Being, I mean, probably in the paper you have mentioned there will be there these details. So I will read it.
Sure.
Thank you very much.
More questions?
So I always, I mean, all these problems, no, it's about the mass of the mass. So I always thought that you have an uncertainty of a factor 2 or 3 when you don't take the skirts of the galaxy. But you come with this idea that it's not a factor 2 but an order of magnitude. So what kind of object do you have in mind? It's an elliptical, but these are not ellipticals. These are like starbursts that we see nearby.
Yeah, but I don't know. The point is that we don't know anything about the structure of these objects.
No.
Anything. I mean, we are starting to detect these objects. So maybe if they were like, I mean, probably they are not, and your measurements are not far away from the real value and so on. But if you just take a normal galaxy today, an elliptical or a spiral or whatever, you really need to sample like at least 5 magnitudes in super brightness, or better if you go to 10 magnitudes in super brightness, to start measuring the effective radius with confidence. Okay?
Yeah.
So, but here at most, maybe you are reaching a range of 2 or 3 magnitudes in super brightness. Okay?
Yeah.
So. I'm not assuming anything, but you are assuming that they are not. For example, have you tried to stack all the infrared data to see whether you find an increase in the size, for example?
Not the infrared.
That would be a good idea, just to be more robust. So.
Yeah, the chi-square image, yeah. The extraction was made using the chi-square. No.
If you, but if you, which was my original question is, if you do the exercise with a spiral today, and you just measure a couple of orders of magnitude around the brightest parts, what is the error that you make in the stellar mass? I'm not sure.
You're observing the bulge?
Yep.
No. We don't have yet the data from the accelerator. Yeah, with Chandra. Chandra. It's coming, yeah. It's not started. Yeah.
Yeah.
Thank you.